Hello and welcome to this lecture in the series Introduction to Algorithms. And today we'll be looking at the recurrences of the type dividing functions, and we'll be seeing that how to solve them. As we have seen in the previous lectures that we take a recurrence and then we first solve it using your recursion tree, and then we solve the same recurrence using your iteration method. So we'll be doing same for your dividing functions. So let us start with an example and see how we will solve it. So if we try to see the time complexity of this algorithm as we have seen earlier in previous examples. So the time complexity of this algorithm Tn will be equal to, this statement will take a constant time, and then this statement will take time taken by this algorithm, but here the size of the problem is n by 2. So now if we look at the recurrence, it will be of this type. T of n will be equal to 1 when your n is equal to 1, and it will be Tn by 2 plus 1 when n will be greater than 1. Okay. So first we will see using your recursion tree how to solve this recurrence. Using recursion tree. Okay. So we will take your initial problem, that is your Tn. So what it will do is that it will print the n value and it will call Tn by 2. Fine. Then again when this will be called, it will print the value of n and it will be calling Tn by 2 square. Fine. So what we will do is that it will go on up to, we'll say, let's assume that it takes k steps, okay, and after k steps it stops, and at that time it will be Tn by 2 raised power k. Fine. So if we see how much time it will take, this will take 1 unit of time, this will take 1, this will take so on, and this will take 1. So what we have to do is that we have to simply add this time. Okay. So we have to add 1 plus 1 plus 1, so on. How many times? K times. Okay. So your T of n will be equal to this. And if we add it, it will be k. Now what we have to do is that we have to calculate the value of k in terms of your n. Now if we look here, this is your stopping condition, that is Tn by 2 raised power k. So what is the stopping condition here? 1. So our stopping condition is n by 2 raised power k will be equal to 1. Fine. So which will mean that 2 raised power k equal to n or k equal to log of n. We have seen this in previous examples as well. So if we'll substitute here, so T of n will be equal to log n, and therefore it is order of log n. Fine. So now we'll be solving same recurrence using your iteration method. So what we do for iteration method is that we open this, that is T of n is equal to Tn by 2 plus 1. What we'll do is that we will substitute the value of Tn by 2 here. So it will be equal to Tn by 2 square plus 1, and then outside is your plus 1. Okay. So it will be equal to Tn by 2 square plus 2. Fine. Again we'll substitute this value here, we'll be using it. So it will be Tn by 2 cube, because we are substituting for n, we are substituting n by 2 square. So 2 square multiplied by 2 will be 2 cube. So n by 2 cube plus this 1, and outside we are having this 2. Okay, so it will be equal to Tn by 2 cube plus 3. So we have a pattern here. What is the pattern? Pattern is that we are having Tn by 2 raised power something plus that same value. So it will go on, if we keep on substituting, it will go on, and finally we will get T of n will be equal to T of n by 2 raised power k plus k. Fine? Here. So now we know that when will it stop? It will stop when n will be equal to 1. Same as we did in your tree. Okay. So here, stopping condition. What is your stopping condition? Here the stopping condition is n by 2 raised power k equals 1. So again, like we did before, 2 raised power k will be equal to n, which will imply k equal to log of n. So we'll substitute this value here. Fine. So we'll get T of n will be equal to T, this will be T of 1 and that will be 1. I'll write here T of 1 plus log of n. This T of 1 is 1, so it will be log of n plus 1. And therefore, what will be the order? It will be of the order log of n. So we got the same order when we solve this recurrence using your tree method. So like I have said in previous examples as well, the iteration method and tree method, they are very closely related. They are almost same. And the only difference is that here you open this statement and here you draw it graphically, you show that how that problem will be divided into sub-problems. Okay. So now we will see another example for same dividing functions. So now we will see another example. Say we are having same algorithm, say display, okay, int n. So I'm just writing here algorithm like I said previously in I'm using the syntax of C language, but here you can see algo is not defined in C, but we are using somewhat a sort of algorithm, you can call it pseudo code. So that's why I'm writing here algo. You can write wide if you want to write perfectly in the syntax of C language, but that doesn't matter. Syntax is not our concern. Our concern is to see how to first form the recurrence and then how to solve it. Okay. So again, if n is greater than 1, so what we will do? So here, instead of printing n one time, I'm printing it n times. Okay. So again, I'm using here printf statement. It doesn't matter. You can use any statements here. Number of statements you can use. It's just to show you how things go. And once this statement is done, I'll be calling the same function display with the value n by 2. Fine. So now let us calculate the time taken by this. So here this will be t of n. Fine. So this will be executed how many times? It will be executed n times. And finally this will be calculated or executed n by 2 times. Fine. So for n greater than 1, we are having this the running time, and for n equal to 1, we are having constant time, that's 1. So what's the recurrence we have? The recurrence is something like this. It is equal to 1 when n is equal to 1. Fine. And it is equal to Tn by 2 plus n. Tn by 2 plus n when n is greater than 1. Fine. So now we'll solve it first using your recursion tree. So we will solve it using recursion tree. Fine. So what will happen is that we are having your root problem, that is t of n. So what it will do, it will execute n times plus it will call Tn by 2. Fine. So here what will happen? It will go for how much time? It will go for Tn by 2. So it will only go for n by 2 time and plus it will call Tn by 2 square. Fine. Again, it will go for n by 2 square times and it will call n by 2 cube. Fine. So this will keep on going how many times? Say k times. Unless we reach where? We reach Tn by 2 raised power k. Fine. So now what we have to do is that we have to sum this in order to find what is the actual running time complexity of this algorithm. We have to just sum up these. Okay. So if we add up these, your T of n will be equal to n plus n by 2 plus n by 2 square plus so on n by 2 raised power k. Fine. So what we can do here, we can take this n common. So it will be n 1 plus 1 by 2 plus 1 by 2 square plus 1 by 2 cube plus so on 1 by 2 raised power k. Fine. So if we look at this series, the sum of this series is actually equal to 1. Means if you are taking, if I show it like this, it will be 1 by 2, then plus 1 by 4 or 1 by 2 square you can write here. And so on, if you will go and you will add up this series, it will be equal to 1. So what we can do is that we can simply write here what? It is equal to 1. So if you multiply it, it will be n. So we directly got T of n is equal to n, which means it is order of n. Fine. So when we solve this recurrence using your recursion tree method, we got that your T of n is equal to n, which simply means that it is order of n. Now we'll solve same recurrence using your iteration method. Fine. So what we'll do is that we'll simply write your T of n, it is equal to Tn by 2 plus n. Okay. Now we'll substitute this n by 2 here. So it will be equal to Tn by 2 square plus n by 2 plus n. Fine. So it will be equal to Tn by 2 square plus n by 2 plus n. Fine. Now I'll substitute Tn by 2 square here, okay, or I'll open it. I'll go for another iteration and it will be equal to Tn by 2 cube plus n by 2 square, and outside these two terms will remain as they were. It will be plus n by 2 plus n. Okay. So it will be equal to Tn by 2 cube plus n by 2 square plus n by 2 plus n. I can go again another step, but I think we have a pattern here, we can see it. So we are having Tn by 2 raised power something, then we have to plus it, plus with it, n by 2 square means whatever value is here minus 1, that is 2. And then we have to go just progressively, we have to keep on decreasing power of 2. Fine. So if I write a general form for this Tn after k steps, it will look something like this. This equation I am rewriting after k steps, okay? After k steps. What do we get? We get T of n is equal to Tn by 2 raised power k. It is Tn by 2 raised power k. Now here plus n by 2 raised power k minus 1, because here it was 3, here it was 2. So plus n by 2 raised power k minus 1 here. Then plus n by 2 raised power k minus 2. And it will go on up to where? N by 2 plus n. It will go on n by 2 plus n. Okay. So we know stopping condition is that n by 2 raised power k is equal to 1. So it will mean that t raised power n will be equal, this will be equal to 1. Okay. Plus, for these terms, I again take the common term, that is your n. So if I take n outside, so inside it will remain 1 by 2 raised power k minus 1 plus 1 by 2 raised power k minus 2 plus so on plus 1 by 4 plus 1 by 2 plus 1. Okay. So like I said before, this is your, what is this? This series again equals, the summation of this series again equals to 1. So it will be equal to 1 plus n. So this series up to here is 1, and then that plus 1 is there. Okay. So now it will be equal to 1 plus 1 is 2, that is 2n. So t of n is equal to 2n plus 1 or 1 plus 1, whichever way you call it, doesn't matter. So therefore, it is order of n. So this is the exact same result that we got in terms of your recursion tree. Okay. So you can see that when we solved it using recursion tree, we got t of n equal to n, but here we got t of n equal to 2n plus 1. So although the higher order term is here again n, so the order is same, but when you solve recurrence using your iteration method, so it's obvious that you will get a more closer result. Okay, you will also get lower order terms. In terms of your recursion tree, you get the higher order terms, and sometimes you can get lower order terms, but not always. Fine. So, but it doesn't matter. Why? Because we are only concerned about your higher order term, that is n, and it is same in both your recursion as well as your iteration method. So now we will see another example and solve it using first using your recursion tree and then using your iteration method. So now we will see another example and we'll see how to solve it using your recursion tree method first. Okay. So I can write wide or I can write algo, whatever you are comfortable with. Fine. So I'll simply write the condition if n is greater than 1, then what you have to do is that I'll use the loop again. And here I'll be writing printf. So it's not necessary. I will write here. You can write any statement over here. Okay? Doesn't matter. So after that, what I am doing, I'll be calling display n by 2, and again I'll be calling display n by 2. So what will be the running time complexity here if you try to compute it? It will be t of n. Okay. For this it will be n. It will run n times, whatever the value of n is. And this will run for t n by 2, and this again will run for t n by 2. Fine. So these three values, that is 2t n by 2 plus n, will be executed when your n is greater than 1. So we have a recurrence, that is t of n is equal to 1 when n equal to 1. Fine. And t of n is equal to 2t n by 2 plus n when n is greater than 1. Fine. So now we'll be solving this recurrence using your tree method, recursion tree method. Solving using recursion tree. Okay. So how will our recursion tree look like? So at the top it will be t of n. Fine. And then what will happen is that first it will print n times it will print. Then it will call t n by 2 and it will again call t n by 2. Fine. Now what will happen? This will first print n by 2 times. Fine. Then it will call t n by 2 square and t n by 2 square. Fine. Same thing will happen over here. It will go for n by 2 times, then it will call t n by 2 square, and it will again call t n by 2 square. Okay. Now what will happen here? It will first print n by 2 square times. Fine. Then it will call t n by 2 cube and t n by 2 cube. Fine. Same will happen here. N by 2 square times. I'm not writing these two because it will just mess up things over here. This will call t n by 2 square and this will execute n by 2 square times. Plus it will call t n by cube. This one will call 2 times t n by cube. This one will call 2 times t n by cube. This one will call 2 times t n by cube. So I'm not writing those two calls here. Okay, so those two calls everywhere I'm not writing because I want to show something else. So what I'm trying to show is that here this statement is executed how many times? N times. Here it is executed n by 2 plus n by 2. That is 2n by 2, that is again equal to n times. Fine. Here the statement will be executed n by 2 square plus n by 2 square plus n by 2 square plus n by 2 square. That is 4 times n by 2 square. So this will be cancelled and it's again n times. Fine. So what will happen is that after k steps, this will stop. But what will be the value at that time? The value will be t n by 2 raised power k. That will be it will be called n by 2 raised power k times, This will be called there will be a whole bunch of t n by 2 raised power k, but I'm just writing one there that we have to solve. So here what will happen is that again here it will be k n by 2 raised power k n by 2 raised power k. So this 2 raised power k and 2 raised power k will get cancelled. It will be only the total time will be n. So if I add the total time, what will we get? We will get t of n is equal to n plus n how many times? K times. Fine. So what does that mean? It means that your t of n will be equal to n k times. Fine. Now this is your equation 1. We have to find the value of k in terms of n. Where will we get that? From here. Okay. So here the stopping condition is that n by 2 raised power k equal to 1. Isn't it? This is the stopping condition. That is your t of 1. So it will imply that k is equal to log n. Now all we have to do is substitute value of this k into this equation 1. Fine. So if we substitute value of k here, so t of n will be equal to n log n. And that gives us the time complexity. Therefore, it is order of n log n. Fine. So we got the running time complexity of this algorithm, which was shown in the form of a recurrence. which is of the order n log n. So now we'll be solving same example using your iteration method. So what we'll do in iteration method is that we'll simply use this t of n is equal to 2t n by 2 plus n. Fine. So we'll be opening this thing, we'll be substituting here, or we'll be using another iteration, that is 2, this t n by 2 I'll be substituting here. So it will be 2t n by 2 square, okay, and then plus n, it is n by 2 and plus n. So I'll be multiplying it, it will be 2 square t n by 2 square plus, so this 2 and 2 will get cancelled, n plus n. Fine. So it will be equal to 2 square t n by 2 square plus n is 2n. Fine. I won't open another step because the pattern is obvious. We are having 2 raised power k plus n by 2 raised power k plus k times n. Okay. So if I go k times, we'll be having 2 raised power k t n by 2 raised power k and plus 2n, sorry, kn. So this is your equation 1. Now what we have to do is that we have to find value of k in terms of n. So here stopping condition is, what is the stopping condition? The stopping condition is n by 2 raised power k, that we have seen in previous examples as well. So n by 2 raised power k will be equal to 1. Okay, here it will be equal to 1. So it will imply that k equal to log of n. Fine. What we'll do is that we'll substitute that value in this equation. So 2 raised power k, if we look here, 2 raised power k will be equal to n here. Okay. So 2 raised power k will be equal to n plus your k will be equal to log n. So what we will get t of n is equal to, first we have 2 raised power k, so n, then t of n by 2 raised power k. So n by 2 raised power k is 1, so it will be t of 1, then plus k here. So what is k? K is your log n and multiplied by n. Okay. So it will be equal to n, t of 1 is 1 plus n log n. So your t of n is n plus n log n, and it will imply that it is of the order n log n. This is the same value that we got when we solved this recurrence using your recursion tree method. So again you can see the difference here. There we got n log n, here we got n plus n log n. So we got lower term as well, so this one is more accurate, but we are only concerned about the higher order term and we are looking at the big O notation, and that is n log n. So this completes your the procedure of or the methods of solving your recurrences when we have dividing functions. So in today's lecture we saw some examples in which we saw those recurrences which were given by dividing functions, means here we had n divided by some value. Okay, sometimes we had coefficient, sometimes we didn't had, but all the examples that we took, they were dividing functions, means the value here was dividing, and we saw how to solve them using your recursion tree and iteration method. I hope that you understood today's lecture and that you will continue your studies in this series. Thank you.